Hello and welcome to another video. In this video, I'll be covering how to use my Sprite animation plugin that I created for Bevy. I'm doing this video despite not having finished my Bevy user input series yet, because it was requested by Veritasen on Discord. If you'd like to make other requests, you can find my Discord by going over to the Bevy Discord group and finding me there. In this video, I'll basically be covering how the example works and how you might expand this to cover your game condition. In the example, you'll be greeted when you run it by this zombie standing here. If you press space, the zombie will attack. If you press up, the zombie will get faster. If the zombie is in its walk or idle state, you can swap its direction. If you press down while in its idle state, it will fall. If you press up again, it'll stand back up. The zombie's state is driven partially by the animation system. This means that the animation system will set the state back to the correct state after it reaches a certain point in the animation, or can set other flags that you could programmatically use in order to operate your game. This allows me to do things such as make it so that once the zombie is falling, you cannot stand up until the zombie has actually finished falling. This can be done and much more easier to represent when you actually run the example yourself and know what keys are being pressed. The other thing this allows is that I can still make it so that if the zombie is standing up, I can press down and the zombie will fall. This is done by inverting the index of the animation. Before I go into explaining how to use the plugin, I need to cover a bit of terminology. I use attributes, which for this plugin is just a wrapper around a U64. Attributes are used to distinguish bits of data internally inside a state of an animation. At the moment, there are currently 3 different flavors of attribute. The core, these are reserved primarily by the crate in order to be able to perform certain functions, whether to flip the X and whether to flip the Y. Things like this will be reserved into the bottom 256. There is then the bottom 16 bits, which represents index. So anything that is greater than 255, but less than the maximum 16-bit number, is used to represent indexes for iterating through things like index nodes, and are simply distinguished from everything else so that there is a guarantee that the values stored at these attributes will be a U size. You can use index nodes however you feel fit, as long as you are only storing U sizes inside that attribute. If you need to store something other than a U size inside a animation state, you should use a custom attribute, which will represent any number greater than the maximum 16-bit number. There are a few ways to get an attribute. You can use new index, which will register the index's name inside a dictionary so that future use, when it's printed out, it has a name. This will return an index node representation as a hash of the name provided. You can use a new attribute, which will do the same, but returning a non-truncated version so that it can be anywhere in the space, but is guaranteed not to be the lower 16 bits only. And then there is from string, which will pass a string and pull out whether it's an index or a custom attribute, or whether it is just one of the core values. And if it is none of those, we'll simply pass it as if it was just a name and then give you a custom attribute back. The next important struct that you need to be aware of is the NodeID. This is, again, just a wrapper around a U64. This NodeID represents the node's unique identifier inside a tree. Primary way you can get this is from a U64 if you intend to use a specific number for a node, or these IDs will be generated by hashing the name of the node. You can also get one from string. This will check to see if the value we're giving is a NodeID and will check whether it is a hexadecimal encoding or a name, and then use the appropriate method in order to acquire the NodeID. The bottom max U64 has been reserved for numbers set by the user. This isn't to say that you can't use NodeIDs greater than these numbers for custom IDs, but simply that hashing a name will never return a value less than that, so you don't have to worry about conflicts when specifying NodeIDs with low numbers. There's also the StartNode. The StartNode is used by the plugin to distinguish which node in the tree is the first node for this object to start at. It is simply a wrapper around a NodeID. A start node can be got with the from string or from U64, which will call the corresponding function on the node ID and create a new start node with that node ID encoded. Up next is the animation state. This is basically just an advanced extension of a hash map that contains an attribute and a list of data that that attribute holds. This also contains a hash set of changed and temporary, which hold data information that is important for other functionality provided by the plugin, such as if a attribute was changed the last frame by the animation system, and if the attribute should be cleared if not changed by the previous animation. This is used for resetting indexes if, say, they're not being used, so that the next time that animation starts, it'll start from 0. If the feature RON is enabled, there is also a data type, which is really hacked together and is my attempt to allow for deserialization of anonymous types. The way that this works is that an attribute will set a RON deserializer when it is first set, and then if set from something like a script, we'll use that RON deserializer to infer the type that it was previously set to. This is probably not the best approach, but is the only approach I know how to do at the moment. So anyone with a pull request, welcome to make that better. The animation state has a few functions, some of which I've expanded to make more functionality. There's the get attribute, which will takes in a type parameter of D, where D is deserialized owned, and takes in the key attribute and will return the D values stored in that attribute. This is similar to the query's single function in Bevy, where it will panic if it doesn't have a value set, if it fails to deserialize. There is the try get attribute, which is the same but will return an option if it fails, and the try get or error, which is the same again but will actually return a error result so that you can debug your code. The get attribute raw will return the bytes without deserializing. This was originally, and probably still is, a bit of a hack for doing things without knowing the type. You can get the raw bytes. This also has the try function, and there's also a mutable version that will let you get access to these bytes mutable. This, again, was originally added for anonymous type deserialization, where the scripts would take in a binary representation of the data that they were setting and would overwrite the type. This was very highly error-prone, and is why I've implemented the RON version. But this version will work even without the RON feature enabled. The set attribute takes in a attribute as the key and a value that can be serialized and serialized owned if the RON feature is enabled. This is where it generates the RON deserializing function. So if you are not using the RON feature, it does not need to be deserializable. That is purely so that the RON can actually run its anonymous type. The only reason it needs to be deserialized owned here is so that RON can infer its type and create a deserializer that I then store for later use, and is only required if you have the RON feature enabled. There is then also the set attribute from RON if you have the RON feature enabled, which takes in a string instead of a value and will deserialize that string. This also has the set persistent and set temporary values. These will add or remove the type from the temporary hash map. Any value stored in the temporary hash map is cleared if it wasn't changed. This will result in indexes being set back to 0 or booleans being removed. There is also a changed function which is given an attribute and will return the boolean whether the hash map contains that change, or the clear attribute which will remove the attribute from the dataset. Finally, before we move on to the actual nodes themselves, is the animation NodeTree. This takes in a generic parameter, which is the flag used to distinguish this tree from other node trees. The node tree consists of a hash map of nodes that are boxed up, allowing for new nodes to be added without having to break the tree. There is also, if you have serialization enabled, loaders, which are used to load node types when you're trying to deserialize from a file. The animation node tree has the functions getNode, addNode, and insertNode used for manipulating the nodes in the tree. GetNode returns an option to the node box at that location. AddNode will add a node that will self-assign an ID and then return the ID that it was assigned. Insert node will allow you to specify the node ID to put this node. Serialize, when provided with an asset server, will return a string representation of this node tree, which can then later be loaded into a separate node tree or stored for future use. It needs access to an asset server in order to get the fixed paths of the frames in things like the index node. Register node is used to add nodes that are not standard to a node tree so that they can be deserialized. This is used primarily with the standard plugin to allow you to deserialize things like a match node with a custom enum, since you need to register the node with the custom enum or it won't know how to use that enum. Load will take a file path and an asset server and load the node, or if it is a node tree, load the entire node tree. There are also corresponding functions for loading individual nodes and node trees from strings. Currently implemented into this plugin are 4 different types of nodes. Index nodes, which return a frame to be displayed. These nodes are your typical sprite sheet animation, where they will simply run through in order their animation. FPS nodes, which are used to specify the frame rate of the animation and will then move on to the next node. Match nodes, which use the attribute provided and will move on to the next node based on the value it finds at that attribute. And a script node, which allows for a very basic script to be written that can be executed and serialized at runtime, allowing you to manipulate attributes based on what other attributes are set to. All these nodes implement the animation node trait, which if you want to add your own animation nodes, is what you would implement. This consists of a run function, which takes a self and the state of the animation and returns a node result, which is either the next node to go to, done containing the frame that should be displayed, or error, which contains a string that can be presented to the user, in which case no update to the sprite will be made. A name, which is the representation that should be presented when querying for the name of the node. If the inspector feature is enabled, a UI implementation so that it can be displayed in the inspector. An ID, which is just the node ID that is used by default. The default implementation of this is to simply hash the name. Serialization, which the default implementation is to simply specify that it is not yet implemented, and then the node type. Serialization is given reference to a mutable string and the asset server, and must append itself to the end of that string. Node type returns a string representing the node's type. This is used for accessing things like loaders. If you have the hash config feature enabled, then you also have the hash function, which just returns the U64. It is also possible to implement the canLoad trait, which will just give access to a node loader dynamic box. This is used for deserialization purpose. And again, if anyone has any better suggestions, a pull request would be much appreciated. If you create any nodes that you think would be useful for everyone, please feel free to make a pull request and I will add those nodes. Okay. Finally, we get to move on to how the example is actually. Primarily, the example just creates a new Bevy application and adds the default plugin. Then I add the plugin Your Animation plugin, which is where I would run generic logic that is related to you interacting with the animation system. Then you add Sprite Animation plugin with the parameter being provided that is the flag that you use to distinguish your animation nodes from something else. Say if you had zombies and players had 2 separate animation nodes, but you wanted the trees to be laid out in the same way, you would use an animation with the zombie animations and with the player animations and give them both different flags. Then there's the setup animation, which just is a system that sets everything up, and then player controller that will allow you to change animation states. The zombie struct is purely just a flag that indicates that this is a zombie and should be animated with the zombie animation struct. In the setup animation, we get access to our animation node tree as a mutable resource and the asset server. We then spawn in ourselves an orthographic camera and dereference our node tree so that we can register the match node of Z state. We have to do this dereferencing because of Bevy's borrow checker not liking mutable references accessing certain fields. Here, I have an example of how you can programmatically generate a node. This is done by loading all of the images that the node consists of into a vector here by going asset_server.load and requesting each file. I then go to the node tree and insert at index ID 3 the index node called testNode with these images and tell it that it is. This will add that node to the tree at that specified location. I then create 3 new index attributes: fall, stand, and attack. I use these to allow for things like the falling animation and standing animation to always start from their 0th index if they weren't already running, and the attack animation to always start from the beginning, even if the attack was interrupted. I then load the node. For debugging purposes, I print out the error if it is not successful. This is done by saying nodes.load and then the path and the asset server. I then load the node tree for the zombie. The test node is where I currently have the FPS node loaded, and then the zombie, which has its own logic. Next, I set up the animation's starting condition. So I initiate a new animation state using animation state default. I then set the fall, stand, and attack to be temporary. This will result in them being set to 0 if they're not updated in the previous run through of the animation. This is useful for clearing out indexes that need to be reset, or if you have a flag, such as a specific point in the animation where something may happen or you need to react, like a sound being played, you would set them as temporary so that they are cleared when they are not specified. I then spawn a sprite bundle in and make it nice and large so that it can be seen easily on screen. I add the flag so that the animation system can easily find this component. I insert the zombie's starting state. I provide the animation state, add the player flag, and then specify that each update of the animation, this object is to start at node 0. Inside the test node, as you can see, I've specified a node ID of 0 to be an FPS node with a frame rate of 7 and the name zombie FPS. The then specified is the next node to be used once this node has been run. In this case, node 1. If we head over to the zombie node tree, it has a node ID specified of 1 being a match node of zombie animation Z state. This has the name of zombie1 switch node. It will check the attribute zombie state, and if it fails to find this attribute, or if it doesn't find a match, it will default to this particular node, which, as seen here, is the idle node. It will then match these pairs, being laying F being this node, idle being this node. So basically the result it gets out of the zombie state will pick which of these it does. It also has test, which will return node 3. As you can note, I'm using low numbers for values that I am manually setting and are not automatically generated node IDs like these ones. This is fine because these values are protected with the node IDs. It is a good way for setting things up for when you need specified nodes that do not need to be generated. Then we have each node, which in this case, they are not given node IDs to begin with, separated by a semicolon here, so they will use their default node ID. They are then given a name, frames, and isLoop, because they're an index node, and then what index they are looking at, which in this case is 256. I also have at the top 5 script nodes which are loaded. These nodes are used primarily for setting the falling and standing animation timing and the attacks to back to idle or laying when they hit that corresponding point. They have an ID identifying themselves. The fallback node, which is used if at any point the script panics, it will simply return the fallback node. Then the script itself. If index stand is greater than or equal to 6, set attribute zombie state to ron idle. What this does is runs the script. If the index state, which will request the stand index, and it's greater than or equal to 6, it'll set the attribute zombie state to ron idle, which will deserialize value between the parentheses into a ron value and set that, and then we'll return the next node to use. In this case, because it is using stand, it will return the stand. These scripts exist for standing forward, standing backwards, the attack, and the falling forward and falling backwards node, which set the state to laying and idle, respectively. If you would like a more detailed view of how these nodes are working, you can find the link to the GitHub repository in the description. Inside the Your Animation plugin, this is where certain logic is specified to run before the animation updates and after the animation updates. These functions are examples of how you might add or remove information from a state. In the zombie state update example, I get every animation state that has a zombie state that has changed. I then set an attribute from string of zombie state. Then for each state, I iterate and set its attribute to the zombie's current state. This is done before the animation runs, resulting in the animation always picking the correct zombie position for the animation. The zombie update state is the inverse of this. It will check to see if the state has changed what the zombie state should be, and then update the zombie state accordingly. This allows you to have code react to specific points in the animation, such as, in this case, when the zombie finishes standing up, it resets their state to standing. You could also have this, for example, if at a particular point an animation is to play a sound, such as a footstep. This can be done by setting an attribute such as play footstep true every time the footstep should be played. This would allow you to programmatically check each animation state and see if it needs to play a footstep. The player plugin simply adds the player animation update function. This function stores in a local variable 3 attributes representing the stand and fall index and the zombie's state. This is where the logic is. If you press A or left, it'll flip the sprite. If you press D or right, it'll unflip the sprite. If you press either of the shifts or up, it'll increment the speed that the zombie is doing. This is simply done by a match statement incrementing to the next appropriate state. This is also where the logic is implemented, that if the zombie is falling, it cannot change states. This is done by falling resulting in changing to falling. This is also results in standing changing to standing. This prevents you from being able to change from one state to another unless the state has actually finished. This is facilitated by the fact that the animation node actually sets its state to idle when the animation finishes. The same logic is applied for falling down, except this allows for that functionality that I displayed earlier, where partway through the standing up animation, you can make them fall down again. This is done by taking the index into the standing up animation that we are currently at, and using that to set the falling index equal to the reciprocal, being 6 minus the index, which means that if you're 1 frame from being fully stood up, you are now 5 frames away from being all the way fallen down. So this allows for you to fall from any point in the animation. There is also a spacebar that sets your mode to attack. This, because it does no other checks, will always result in the animation immediately jumping to the attack animation, regardless of the current state of the animation. There is also the T button, which will set it into test mode, which will just run through all the animations with that programmatically generated node that we showed earlier. At the very end, I set the animation's attribute 0 to its zombie state. This is not actually necessary because of the inclusion of the other plugin, which does this automatically. But this is to represent that you can set these attributes. Thank you for watching this video to the end. Please like, comment, and subscribe. And feel free to ask any questions in the description, or post a issue on GitHub if you would like to see a feature added or modified, or even just something more clarified in the documentation. I'd like to thank PhaestusFox again for suggesting making this video. And I would love to see anyone's work that they make using my plugin. I'm really interested to see how it is going to be used in an actual game. And I will see you all in the next video. Thank you. Please like, comment, subscribe.